Let's welcome the speaker.
Thanks. The title of my talk is Matrix Product Codes over Finite Commutative Rings. And this is based on a joint work with Professor Fan and Professor Lin. Here is the outline. Okay, the first I want to introduce some construction of codes. Before we introduce the construction of the codes, I want to give some general introduction about the coding theory. First, I let FQN denote the vector space over a finite field FQ, and any subset of FQN is called a code. And below in FQN we have the Euclidean inner product that is defined in this way, that you take two vectors and we define their inner product is to be the x1 times y1 plus up to xn times yn. And by using the inner product, we can define the dual code. That is these cases. And also, we have the self-dual. If the code C is a subset of the C perf, that is, code C is a subset of the dual code, then we see C is a self-orthogonal. And if they are the same, then we say it's a self-dual. And here is a minimum Ham distance for a code C. We can define the minimum Ham distance and the minimum Ham weight. And if C is linear, we know that here C is linear is the subspace of FQN. If C is linear, then the minimum Ham distance and the minimum Ham weight of C is the same. Okay, now we can introduce the construction of codes. There are many known methods for constructing longer codes from short ones. For example, we have the Plotkin's construction, that is mu plus v construction. Here we have two codes, C1, C2, and we can construct in this way. So for the constructed code, Plotkin gave this construction about the parameters. That is, here is the constructed code, the length, and this is the size of the real code, and this is the minimal Ham distance for the constructed code. And this construction can be rewritten as a following form. That is, we can write this form as this matrix product. And there is another construction. For example, here is also volume, is u plus v plus w, and 2 mu plus v and the v construction. And for this construction, we also have the parameters. The length is 3 times n, and this is the size. That is C1. This is the size of C1, and this size C2, size C3. And no. So let me say U V. Yeah, two. Yeah, right. Sorry. So we have this construction, and this construction also can write in this way. And there is another volume construction, is a Turyn's construction. For this construction, it is A plus X, B plus X, A plus B plus X. For this construction, we can also write in the matrix product forms like this. And for this construction, we also have the, is a Hamming distance for this construction, which given by Falling. That is, they give the upper bound for this construction and the lower bound for the construction. And this can be found from these people. So, in 2001, Blackmore and Norton, they generalized these three constructions. There are also many other constructions to a more general setting. That is, if we have M codes with the parameters, the length is the same, and the size mj for each cj, and for a matrix with the size m times L over Fq, then we can construct matrix product codes as the following. That is, a matrix product code over a finite field Fq is a set of all the matrix products. That is, we can write this. Here, each CJ is writing in the column vectors. So this is a matrix product codes. So for the constructed codes, how to determine their parameters? That is, we want to know for the constructed codes, their parameters. For example, the length and the size, and we are more care about the minimum Hamming distance or minimum distance. That is very important for the code. Before we give some results, we want to show the three matrices which we just given before. The first matrix is related to the Plotkin's construction, and the second, and this is related to the Turyn's construction. If you see the first two matrices, if we take the first row of the two matrices and consider the 1 times 1 submatrices, we find they are non-singular. If you take the first row and consider the first 1 times 1 submatrices, you will find they are all non-singular. And if you take the first two rows, A and B, the first two rows, and consider the 2 times 2 submatrices. For example, for this matrix A, we take the whole A, so it's non-singular since the determinant of this matrices is 1 determinant. And if you take the two matrices, you consider the first two columns and the last two columns, or the first column and the last column, we found they are non-singular. So, but this is a little different. For this is like little different. So observe this observation, we Blackmore and Norton introduced the following concepts. That is, an M times L matrix is called non-singular by columns matrices. If you take LK, K is less than or equal to M, and is greater than or equal to 1, and add K columns, and we can get as submatrices. If the determinant of these submatrices is non-zero, then we call these matrices is non-singular by column. And here is another notation. A matrix is called a triangular if it is a column permutation to an upper triangular matrices. We will be used in the following. So by using the special matrices that is non-singular by column matrices, Blackmore and Norton give the following results. That is, take M codes Ck k from 1 to to M, and they get this result. That if A is an M times L non-singular by column matrices over FQ, then C is a code with the parameters. That is, this is the length, and this is the size, and this is the minimum Ham distance. And for the minimum Ham distance, they give the following lower bound. They can bound the code, the construct code with this bound. That is L minus K plus 1 times the minimum Ham distance of Ck. And furthermore, if A is a square non-singular by column, then for the dual codes, they also have the bound the minimum Ham distance. If A is a triangular, then they can meet the two equalities above hold. That is, here we can with the identity, and this was appeared in AAECC in 2001. And in 2008, when Asch, they generalized the matrix product codes to finite chain ring cases, and he used the different distance, different weights. That is, he used the homogeneous weight over finite chain rings. And he gives this result. That R is a finite chain ring, and Ck with the parameters here is a minimal homogeneous distance of Ck. Then, if A is a non-singular by column, and the construct code C with this kind of parameters, length, size, the minimum homogeneous weight, homogeneous distance, and it satisfies this lower bound. And also, if A is an M times M square matrices, then for the dual codes, they also have the similar result. And if A is triangular, you see, that is, we can meet the bound here. And this also published in AAECC in 2008. So, what are we going to do? In the following, in this talk, I will discuss the properties of matrix product codes over finite commutative Frobenius rings, and bound the minimum distance of matrix product codes constructed with several types of matrices in different ways. And we also have the third. In order to do this, we need to introduce some notations. Here, R is a finite commutative range with identity 1 not equal to 0. And if you write the identity element 1 of the ring R as the sum of the primitive idempotencies of R, then we can obtain an isomorphism. And with this, isomorphism, here, these are all local rings. We identify the elements in R with this form. And R is called a Frobenius. So if we want to consider the dual codes, we want to use some properties of the Frobenius rings. So we give one definition. R is called Frobenius if the perp of C perp is equal to C. Here C perp is a dual code of C. For any submodulus C or for any free R or modulus Rn, then we can or.
And for which rings do we have 2-1? For any ring we have 2-1?
Which?
Previous slide.
Previous slide. This one?
Yeah, this is true for
any commutative rings. Here we don't need Frobenius. We in this talk we want to use this properties of the Frobenius rings. That is, R is Frobenius. Then we can get the cardinality of C perp times the cardinality of C is equal to the whole cardinality of Rn. So why is we use the Frobenius ring to coding theory? Hence, J Wood proved that the Magnus identity and the Magnus extension theory hold in Frobenius rings. And with the isomorphism 2.1, R is Frobenius if and only if each local component Ri is Frobenius. This is more notations. For a matrix over R, M times R, the size is M times R. We can write with isomorphism. We can write A with this form, and here AK is just Aijk. Here K is from 1 to S. And for the vectors, we also have this form. So here is linear independent for any integer t. Here t is greater than or equal to 1, and we can take t vectors, and we see the t vectors a1 to at to be linear dependent if there exists a vector in the set difference RT slash the zero vector such that their linear combination is 0. So this is a usual way we use it in the linear algebra. Otherwise, the t vectors are said to be linear independent. And we can prove that the t vectors are linear independent if and only if for all k, the t vectors are linear independent in the local rings. And if an R submodel of Rn is generated by vectors, the t vectors which are linear independent, then it is a free R model of rank T, and we see that the T vectors form a basis of the free submodel. Here is some definitions about the matrices, special matrices. We will be used in the next. Given M times L matrices over R, and if the rows of A are linearly independent, then we see A is a full row rank matrix, full rank. And if there is an L times M matrix B, such that A times B is equal to the identity matrix I, then we see A is the right invertible, and B is the right inverse of A. And if A is a square, and the determinant of A is a unit of R, then we see A is a non-singular. And if for any t is is greater than or equal to 1 and less than or equal to m. And any t times t submatrix of the first t rows of A is non-singular. Then we see A is non-singular by columns. If for the last t rows such that they are non-singular, then we see the reversely non-singular by columns. Okay, by using this definition, we have the following proposition. Let A be and 4 rank matrices. That is, the rows are linear independent. And here X is the variables. Then the set of solutions of the linear equation system AX equals 0, then it is free subordinal in RL and with rank L minus L. Sorry. And we also have a 4 rank L minus M times L matrices G over R, whose rows form the basis of this free submodel. Here is an ideal proof. We prove first when R is local. R is local, then we can prove there exists an invariable L times L square matrices P, such that A times P with this form. And we can write AX equals 0 as this form, and then we can find this result holds. And then by using the identity, we can from the local to the general cases. Here's more definitions. A is M times L matrices, and for L index K, which is in L index K, we let UAK denote the linear code generalized by the ith rows of A. For example, if K is 1, that is the first row of A. They generalized a linear code. If K is 2, then the first 2 rows, the first row and the second rows, they generalize the linear codes, and so on. And here, LAK, we denote the linear code generalized by the I rows for I equals K plus 1 to M. For example, if we take K equals 1, that is, we take all the rows of A and they generate a linear code. If we take K is 2, that is from the second row to the bottom, then these rows generalize the linear codes. So it is easy to find the UAM is equal to LA1, and for the convenience we let 0, UA0, just the 0 code, and LM plus 1 is LA is 0. So using the notation above, we can find the set of solution of the linear equation system AX equals to 0 is the dual code of LA, the dual of the LA1. And if A is a 4 rank, then this is the thing. Here the G is just we just defined in the proposition 2.1. Okay, now we want to give a general distance bound for matrix product codes. Given M codes Cj from 1 to M, and with the parameters, the length is n, the size mj, and we also the minimum Ham distance is DHG. Oh, here we don't need to the Ham distance. Here A, we use the forward rank matrices. And for this matrix product codes, we have the first result. Sorry. Assume the notation is given above, and we suppose W is a weight on R. And the construct the matrix product codes, then is a code with the parameters NL, and here is the MG, all the size, the product or MG, and the minimal distance DW. So here we don't need the Ham weight or other weight. It's just the weight is enough for the DW. Then they satisfying the two, two lower bounds. Here it is here is CKH, but here is weight. That is UAK we have defined before. That is we defined for the first K rows way. They generate a linear code, and this is the minimum weight. Here is the ideal proof. Since A is the forward rank, if you say A is the forward rank, we can find the size by using this equation. We can find the size of the size of the code is just the size of each CGS size they time together. So the first result is easy to get. For the second result, we can take any different vectors in C and consider the Hamming distance. They consider not Hamming distance, just related to the weight. So we can write the Cj minus Cj prime equal to Bj, and you can find there is an index k such that the first k minus 1 is 0, but from k is not 0. And so the two vectors C minus C prime equal to this vector, and this vector can write in this form. Here we partition A as by rows. So this is a k row, the kth rows, and this is the m rows of A. So if you, for the vector pk, if you take, notice that the vector pk writes in column form. So if you take non-zero bik, and we can find the weight, the I rows of the weight is this, but this is non-zero since A is a forward rank. So, but if you find this is AKAM, just is generalized, generated a linear code, LAK. So this is non-zero vector, and this is the minimal minimal distance. So we have this is greater than or equal to these values, and you count how many non-zero Bij you can get these results. And the second one is similar. So that is for the general distance bound. Now this result is for the the dual code. Given M codes, And this code, oh sorry, this code will override Frobenius ring R. And let A be a full rank. Then we can prove that since A is full rank, then A have a right inverse. And assume that B is a right inverse of A. And G is the generator matrices of the dual code LA1. That is how to say. That is G is the basis of the A of the set of solutions of a linear equation system AX equals 0. And the set between B and G transpose, the transpose of G. Then we can prove that the dual code is also a matrix product code. That is, C perp is equal to this, has this form. This is C1 perp, this is Cm perp, and this is Rn, here is R minus M. If you write, they can write this form. And here we note that we don't need A to be square. That is M maybe equals to L, or M is not equals to L. Also okay. Here we don't need A to be square. The proof is that is we can prove that this matrix is invertible, and A is M times L submatrix of the inverse of these matrices, and is the first how to say M rows. And we can write C as this form. Since this L minus M is 0, so this doesn't matter. So we can write this. And the following we can show that this contains is a subset of C perp. And then by using the Frobenius properties, R is the Frobenius. So we have that the size of C1 perp times the size of C1 equals to Rn, the size of Rn, by using this. So you can compare the two sides, the size, and the size equal. And we use this since this is a subset of C perp, so they are the same. Now this is for the matrix product code with the related matrices. That is, the matrix A is just a full row rank, and we give a bound for 8 weights. Now in the following, we want to consider more special matrices related to the matrix product code. That is, we will call it the strongly full row rank matrices. So before we introduce our result, I want to give some more definitions and some results. Suppose C is a non-zero code of length over a finite commutative range. Then the following is a single bound over for codes over R. That is the minimum Ham distance of C is less than or equal to n minus this plus this. And if C is free, then the equation becomes the following inequality. And if the equality holds, then we see C is the maximum distance separable code over R, that is MDS code. And for a free code of length n, length L and rank M, we will call it LM code. That is, L is the length and M is the rank. And since is free, so this code has for rank generator matrices. So this is for the strongly full rank matrices. This is the definition. First A should be full rank. And if this code we know that it is from the first row to the M. That is all the rows of A generated a linear code. We denote by UAM. And if this code is an MDS code, that is the length is R, and this is the rank. Then we see A is a strongly full rank matrices. And for T greater than or equal to 2, if there is a sequence of indices satisfied that each UAIH is RMDS, then we say A is A1, I T minus 1 strongly full rank matrices. And when T is equal to 1, A is just a strongly full rank matrix. And we also have the reversely strongly full rank matrix. That is, here we use the UAAH, but here is we use the LAIH. And when T is equal to 1, then A is just a strongly full rank matrix. So for the strongly full rank matrices, we have the following proposition. A is a full rank. Assume that A tilde is an invertible matrix with A as the submatrix consisting of the first M rows. Then the following are equivalent. That is, A is an A1 to AT minus 1 strongly full rank matrices. And the second is the transpose of the inverse of A tilde is a reversely A1 plus 1, AT minus 1 plus 1, M plus 1 strongly full rank matrix. And if the if M equals to R, then it's just this one. So these two statements are equivalent. So by using this proposition, we also can have this corollary. That is, we have defined the line signal by column. So if A is the line signal by column, then A is just 1, 2, 2M minus 1 strongly full rank matrix. And the transpose of the inverse of A tilde is a reverse to M plus 1 strongly full rank matrix. Here is an example. This matrix is related to the volume construction, Turyn's construction, T. And you can find T is a two strongly full rank matrices. That is, again here is a matrices, the first two, and the whole is a. But T is not non-signal. Since if you take the first row and the second column, we get submatrices 1 times 1 submatrix 0. So it is 0, not satisfied the condition of non-signal by column matrices. And T is also a reversely 3 strongly full rank matrix. We can check it. So this is our last result Suppose A is A1 to AT minus 1 strongly folded rank matrices. And here, C1, Cm is the cause of length n. And by using this strongly folded rank matrices and and the M codes, we construct the matrix product codes. And for this product codes, we can get that the length is n times L, and the size is the product of all the size Cj. Moreover, we have the for the minimum Hamming distance, we have this result. That is here the minimum Hamming weight is greater than or equal to the minimum of these integers. And furthermore, if the following three conditions are satisfied, then the equality hold. That is, we can take this. That is, all are linear. And the first A1 is the same. Second, the A2 minus I1 is the same. And CA1 contains, CA2 contains up to contains CIT. Then we can get this become equality. Here is ideal proof. I just want to omit it. The main idea is using the theorem 3.1. Here is the dW. Here is the dW, but we change the W with the Hamming weight. And by using the fact this code is a subset of this code, and this code is a MDS code. So with the minimum Hamming distance L minus AH plus 1, so you can get the first result. For the equality, we need to we can prove there is a block lower triangular matrix Q such that QA is with this form. And then by using the three conditions, we can write C, just this one. And by using equality and the condition 2, we can get here H, we just equal the T from 1 to T. And for the equality, here is greater than or equal to. For the equality, we just need to show for each H there is a vector code word C such that the weight is equal to L minus AH plus 1 times the minimum Hamming distance of CIH. And this is a dual version for theorem 4.1. Here is if A is a reversely, then we have this result. And the proof is the same. It's similar to the proof of the theorem 4.1. Okay, now we want to consider the dual code. When the matrix A is A1 to AT minus 1 strongly folded rank matrices, we want to give the minimum Hamming distance. We want to bound the minimum Hamming distance. So in the following, when net R is a Frobenius ring, and A is a strongly folded rank matrices, and in the following, in the last slash, we have proved that the C perp is this form. And for convenience, we let C, if M is less than L, we let the C M plus 1 perp equal to C L perp equals to Rn, and set A IT plus 1 is L. So here is the result. That is, if we let the notations be as above, and for the matrix product code C, the dual code of C, the minimal Ham distance is bounded by these values. And if the following three conditions are satisfied, then we can get, that is, this inequality becomes equality here. And if M less than L, notice that here is the Rn. So the minimum Hamming weight in Rn is 1. So this AT is M. So this is M plus 1. So the proof, I don't want to give more details. So from this result, we can get the following corollary. That if A is 1, 2, minus M minus 1 stratiform rank matrices. In other words, that is A is a line segment by column. And C1, Cm because over R. And for this matrix product code, we get the following bounds. This is for the code C, and this is for the dual code C. And if C1, Cm are linear, and this condition satisfied, then the equalities are attained in all these inequalities. And this result generalized the result of Blackmore and Norton in 2001, and Van Asch in 2008 from two directions. In Blackmore and Norton paper and Van Asch's paper, they considered finite fields and chain rings, but in these cases we consider the commutative rings. And for the dual codes, they didn't consider the cases when A is non-square. But here we can consider it from square to non-square. That is, we have this result. So this is for the result. Under the last section, we want to introduce some more results. This is related to the Turyn's construction. Turyn's construction, with our result, we can give this bound. With our result, we can obtain this result. And Finite in 1988 gives a Hamming bound we have shown before. But this we have a lower bound. This lower bound. In general, the two lower bounds cannot compare directly. So we want to, we want to generalize the Finite result to more general cases. First, we introduced the matrices. Two-way M prime matrices. That is, if we write A as this form, M prime plus M double prime. If A prime is I prime generated an MDS code, and the A double prime generated a linear code, that is MDS, and the whole A generated a linear code, is MDS. Then we see A is a two-way M prime stratiform rank matrices. By using these special matrices, we can construct a code. That is M prime, M double prime. A is a two-way M prime matrix. Then we can by using our result, we can get this bound for the code C. And for the terms, the lower in these bounds, we have the similar result. That is, if A is a two-way M prime strongly forward rank matrix, then we can get this result. Why we use this? If you watch this matrix T is just two-way matrices. That is 2. The first 2 rows generate the MDS codes, and the last row generate a linear code, which is MDS, and T generate the MDS code. So it's a special cases. T is just a two-way M prime strongly forward rank matrices. It's just this special case. And we have this result. This is an ideal proof. Now we just want to show that an example. That is, we can take the 4 codes, and by using the 4 codes, we can construct the intersection, the direct sum, and give some more information about the construct codes. So by using our results, if we choose C2, C1, and by using the T is a matrix related to the terms construction. So here is the binary failed cases. So we can get, by using 5.1, we get the minimum harm distance, and by using 5.3, we give this minimum harm distance. And there is a 5.4, so we can get the minimum harm distance is 4. And this we can get, take different code, we can get another code, and you can get this code. I just want to emphasize that we just mentioned that the 2 lower bound cannot compare directly. This example to show that. For the first example, you see this is better than this one. But for the second one, you can find this is better than this one. And that's all my talk. I want to thank Professor Plotkin for the invitation and for his hospitality. And I also want to thank CHAOSS for their support. Thank you very much.
Do you have any questions?